Okay, polynomial equations. So polynomial equations, first video in the polynomials topic. A polynomial, P in Z, of degree n in one variable is an expression of the form. So the polynomial in Z, a sub n, z to the power of n is your highest power, plus a sub n minus 1. Notice the z to the n minus 1, one power less. We keep going down. Now, the reason that's just a sub n, it's just the coefficient of the z to the n term, and this n minus 1 down here just means that this coefficient of the n minus 1 term, all right? And going all the way down until you've just got one z left and then basically no z's left. That would be the constant term. So we know z to the power of n, that's the highest power then. That's of degree n. Now, if all the coefficients, a sub n minus 1, etc., a1 down to a0 are real numbers, then we call it a polynomial over the set of real numbers. That's not a complex numbers polynomial. So, for example, if you look at z squared minus 5z plus 1, it's a second degree polynomial. It's got degree 2, because the highest power is 2. It's over the set of real numbers because all the coefficients of the z terms and the constant term there, basically your a, b, c. You know how it's ax squared plus bx plus c for a quadratic? A quadratic is a type of polynomial. So this is a polynomial, second degree polynomial over the set of real numbers. Remember that polynomials have real roots if discriminant's greater than 0, equal roots if discriminant equals 0. Do you remember this? And complex roots if the discriminant's less than 0. In other words, if under the b, where the b squared minus 4ac bit, you know how it's negative b plus or minus the square root of b squared minus 4ac? b squared minus 4ac is the discriminant. If it's less than 0, you have complex roots. Because if, say, it was negative 16, you'd call it 16i squared and then you could square root it. We did that in complex numbers. So if any of the coefficients, so going back to our original polynomial, if a sub n minus 1, etc., any of those coefficients are complex numbers, then the polynomial is a polynomial over the set of complex numbers. An example there at the top of the screen, z cubed, that's got a real coefficient of 1, but z squared has a complex coefficient of I. The z term has, I think that's meant to be, it's definitely not meant to be 2 minus 3. It's probably meant to be 2 minus 3i or something. I have no idea what it's meant to be, but don't worry about it. But there is an I in front of, let's just go 2 minus I or something. That'll do. And the last term is 2. That is a degree 3 polynomial over the set of complex numbers. Okay, because some of the coefficients have got i's in them. They're complex. Now, the fundamental theorem of algebra basically says if your power, if it's z squared, you've got 2 solutions. Z cubed has 3 solutions. Z to the power of 4 polynomial has 4 solutions. So that's what the fundamental theorem of algebra is. It says a polynomial equation, P polynomial of z equal to 0 of degree n has n solutions over the field of complex numbers. Now, every polynomial equation with complex coefficients, where polynomial in z equals 0 of degree n, where n is a positive integer, has a root that's a complex number. So what I'm saying is, if your polynomial is a complex polynomial, it's going to have roots, it will have a root that's a complex number. Real polynomials, like the one I've highlighted there, may or may not have roots that are complex numbers, depending on what's under the discriminant, under the square root sign, depending on what the discriminant is. All right, but any polynomial with complex roots will have a root that is a complex number. So here is, for example, if we have this polynomial here, polynomial in z is a sub n, z to the power of n, all the way down to a0, if that's equal to 0. The fundamental theorem of algebra, for example, if z1 is a root, do you remember the factor theorem and the remainder theorem, girls? If z1 is a root, then if you substitute z1 into that equation, you'll get 0. All right, you did that in the polynomials topic in 3 unit. Okay? Hence, if Z1 is a root of this polynomial up here, then Z minus Z1 would be a factor. Remember that sort of stuff? All right, so therefore that polynomial in Z can now be written as Z minus Z1, I've taken a factor out, times some polynomial Q sub n minus 1, meaning its highest power is only going to be n minus 1 because I've got one factor there, one solution of Z. Like, all right, I'll explain what that means. Do you get that or not really? If you've got a x cubed polynomial and you know that x minus 2 is a factor, hasn't it still got another 2 factors? So it'll be x minus 2 times some x squared polynomial. Does that make sense? If you've got an x to the power of 4 polynomial and you know that x minus 1 is a factor, it'll be x minus 1 times the rest of the polynomial will be x cubed. You still have to factorize the rest of it. So that's what this is saying here. If you've pulled out one factor, then, and this is of degree n, then there's going to be n minus 1 powers left. That's what this q sub n minus 1 z equals 0 is, because q sub n minus 1 z is a polynomial of degree 1. So if it was z to the power of 10 and you pulled out one factor, you still got 9 z to the power of 9 left, and still to factorize. Okay, then if z2 was a root, then another factor would be z minus z2. So you'd have the first factor out, the second factor out, you've still got n minus 2 of powers left, if it's originally powered as n. If you kept continuing that process, you would end up with the polynomial in z, if we fully factorized it, you'd get z minus the first root, z minus the second one, all the way up to z minus the last root equal to 0. You could completely factorize it out. That's what that's saying. Now, there are just some symbols here. Nearly done. We use the symbol C for complex, R for real, and Q for rationals to denote the complex, R for reals and Q for rationals, to denote the complex, real, and rational numbers respectively. Now, what do you think this means? Q. That means it's a subset of R, which is a subset of C. Don't rational numbers belong to real numbers, and real numbers belong to the field of complex numbers? So complex numbers are everything, and then real numbers have the real part but not the imaginary part. And rational numbers can be written as fractions. They're real as well. So we're going to do this example now. So x to the power of 4 minus 2x squared minus 3. we're going to factorize that together over the complex field, the real number field, and the rationals. Okay, so that's what we're going to do first. So find the zeros of that polynomial over the rational numbers. So in other words, rational numbers, whatever solutions, whatever factorizations we do, they have to all be rational. So you might have to stop and not be able to continue and fully factorize, all right? So what have we got? We've got x4 minus 2x squared minus 3. Can anyone think of course it's going to be x squared. Can you think of the numbers that multiply to give -3 but add up to give -2? It must be -3 plus 1, huh? -3 plus 1. Now, so therefore, your polynomial in x is equal to that, which equals that. So therefore, haven't we got that x squared equals, so therefore, I'm going to put that equal to 0. Oh no, I'll go here. So x4 minus 2x squared minus 3 is x squared minus 3x squared plus 1. If I put that equal to 0, what have I got? That x squared is 3 or x squared is -1. Could you get, what's my solution for x squared is 3? Isn't it just plus or minus root 3? Is that a rational number? No. So this has no solutions. So px equals 0 has no solutions over the rational numbers, because the solution's going to be x is plus or minus root 3. And this one's only got a complex number solution. Do you see that? X squared is negative 1 only has a complex number solution. So if you're asked for the zeros or the solutions of this, it's like 2 unit. What can you do in 2 unit? You could do that, and then you would write, oh, actually in 2 unit you'd go plus or minus root 3. But if I'm just saying rational solutions, there are none. So let's just keep going. So we've got, so now we've got x squared minus 3 times x squared plus 1 is 0. So therefore x squared is 3 or x squared is negative 1. This has no rational solution, but this one has the solution x is plus or minus root 3. Get the idea? So therefore x equals plus or minus root 3 over the real numbers. That has no, sorry, I don't mean rational. This has no real solution. That's what I mean. Got it? No rational or real. Real is higher up. That has no rational solution, but it's got no real solution as well. Yeah, because we're trying to solve over the real numbers, so I need to make a conclusion with real. So that's got no real solutions, or no solution over the real numbers. Got it? So now, over the complex numbers, this is what we've got so far. So I'm just going to go x squared minus 3, x squared plus 1 equals 0. I'm going to do my full factorizations. Haven't I got x minus root 3, x plus root 3 if I factorize the x squared minus 3? I'm just going to do it like this. And isn't x squared plus 1 the same as x squared minus I squared? Remember, I squared is negative 1. So therefore, this is x minus root 3, x plus root 3. I mean, I could have done it just from there. If x minus I, x plus I. So therefore, the solutions are solutions over the complex numbers are plus or minus root 3, plus or minus I. I could have just continued from here and just gone x squared is negative I, x squared is I squared is negative I squared, x is plus or minus I. But I prefer to factorize it. So they're the solutions over the complex numbers. Do you get the idea? So you really need to look at how they're asking you to find solutions. Is it over the rational numbers, over the real numbers, over the complex numbers? Okay? Now, be careful here. This is very important here. So when factorizing non-monic polynomials, note that if az minus b is a factor, that might be like 2z minus 1, 2z plus 3. You know, not all polynomials have z minus 2, z plus 1 as their factors. Sometimes it's 2z minus 5, you know, whatever. So when factorizing non-monic polynomials, note that if az minus b is a factor of the polynomial, then we know that from the factor theorem that polynomial of b over a equals 0. How do we know that? For example, I'll just show you an example. If az minus b is a factor, then, you know, don't you go, well, that equals 0. What would happen if I rearrange this? I get az is b, therefore z is b on a. That's where that's coming from. All right, so let's have a look here at our second example. It says, example 2, reduce 2z cubed minus 3z squared plus 8z plus 5 to its linear factors over the complex numbers. Linear factors. I don't want factors of z squared in the end. That it has to be z minus, or z plus. No z squared, no z anything else like that. And hence find the values of z for which that is equal to 0. So we've got 2z cubed minus 3z squared plus 8z plus 5. Do you know how you're going to find factors, possible factors of this? Do you remember it from 3 unit? You've got to look at the factors of 2. What are the factors of 2? 1 and 2. So plus or minus 1, plus or minus 2. And the last term. What are the factors of 5? plus or minus 5, plus or minus 1. So you need to be able to so we have to see which combinations of these are going to give us 0 when you substitute it into the polynomial. So remember, we're looking for a factor. We've got to find that first factor. So P of 1, what do you get? 2 minus 3 plus 8 plus 5. That doesn't equal 0. You don't even have to bother working it out. It doesn't equal 0. We're going to try some fractions in a minute. P of minus 1. Let's see. You'd get negative 2 minus 3 minus 8 plus 5. That's not equal to 0 either. All right, let's start trying some fractions. P of a half. So 1 over 2. Okay with this? You've done, so P of 1 over 2, 1 from here, 1 from there. So what have we got? A half. 2 on what? 2 times 1 on 2 cubed is 2 on 8. It's a quarter. Minus 3 times a half squared is 3/4. Plus 8 times a half is 4 plus 5. There's no way that that's equal to 0. Got it? Try P of negative a half. Think the ones you can consider as 1 over 1, 1 over negative 1, or whatever. Then 1 over 2, 1 over negative 2. Negative a half in here gives me, I think, negative a quarter. Negative a half would give me the same result as before, negative 3/4. Negative a half is negative 4 plus 5. I think that is going to give me 0. Got it? That gives me 0. So therefore, how do you get negative a half if you start off like this? So therefore, negative a half is a root. Therefore, what's the factor? How does this form? Wouldn't you have 2z plus 1? Because if you go 2z plus 1 is 0, isn't that negative 1 over 2? Do you see that? Now, what you can also do, so therefore, 2z plus 1 is a factor. Do you get that? Another way you can, just trying to think how you can, you know what you can do? Yes. You know how if negative a half is a root, the other thing you can do, normally you'd write z plus a half, but you're not allowed to write z plus a half as a factor because you always have to have whole numbers as your, so what you can do, if you put a 2 there to balance that, you get 2z plus 1. And now if you put that equal to 0, don't you get negative 1 over 2? So this, by the factor theorem, by the factor theorem, therefore negative a half is a root. Yes. So to know to try a half, you do the factors of the 2 and the factors of the 5. And then you do this of the last one over the first one, a factor of this over a factor of that. All right, so we did 1 over 1 and 1 over negative 1. Then we can do 1 over 2 or negative 1 over 2. You know what I mean? Yeah. And then you could try 5 over 2 would be the last combinations to try. All right, and that's how you know. So if it's a non-monic polynomial, you look at the last term, the constant, and the coefficient of the highest power, and you look at their individual factors, and then you do combinations of them. I'm pretty sure it's always the last one over the first. All right? Well, it's more than likely, sometimes it'll be a fraction. I think it'll more than likely be a fraction. If this was 2, but that was even, that was even, that was even, you'd probably get a whole number thing, maybe. All right? Yeah. So now, we can't put negative a half as, you can't write z minus a half. So, sorry, z plus a half. You know, if minus 1 is a factor, then, if minus 1 is a root, z plus 1 is a factor. So if minus a half is a root, you can say z plus a half. But you're not allowed to have halves. So how am I going to balance out that 2, that half? I put a 2 at the front. 2z plus 1. Or if you rearrange 2z plus 1 and you put it equal to 0, don't you get negative a half? So z equals negative a half. All right, and that's what we do there. So now that we know that 2z plus 1 is a factor, to find the other factors, you divide. We haven't missed any powers there. So let's go. What have we got? Is it z squared? Our first one? Yep. Z squared. So we've got 2z cubed plus z squared. Let's subtract. What do we got? Minus 3 minus 1. Minus 4z squared. Bring down the 8z. What have we got? Minus 2z. Minus 4z squared minus 2z. Subtract. You get 0 and 10z. Bring the plus 5 down. And this must be plus 5. 10z plus 5. Fantastic. It's 0. So therefore, I can factorize my polynomial. So therefore, 2z cubed, I'll just write it up here. Are we ready? Did you get that down? So now, if I've got, that's my polynomial, I can say that that's the same as 2z plus 1 bracket z squared minus 2z plus 5 equals 0. Okay? Now, there is no way that factors of 5 are going to add up to negative 2. So we have to use the quadratic formula to solve the bit for the quadratic bit. So z equals, for this one, negative b, which is 2, plus or minus the square root of b squared, which is 4, minus 4 times 1 times 5 over 2 times 1. So it's 2 plus or minus the square root of 4 minus 20, which is negative 16, over 2, which is 2 plus or minus the square root of 16i squared, over 2, which is 2 plus or minus 4i over 2, which is 1 plus or minus 2i. So therefore, the question is your roots. So therefore, the roots are, what are they? Negative a half, 1 plus 2i, 1 minus 2i, but you have to factorize it. The factored form, so therefore your polynomial in z, written in factored form, is, isn't it 2z plus 1? How do I write my next roots? Z minus, in brackets, 1 plus 2i, z minus 1 minus 2i. And now get rid of those other brackets, z plus 1, z minus 1 minus 2i, z minus, and I need brackets here, 1 plus 2i. There we go.